So let's talk about the first of that kind of pattern, which is the scaling grids. So here what is this pattern is basically here whenever our system grows very becomes very popular, then the read request might grow from hundreds to thousands or millions of users read request. So here the pattern is basically that read traffic whatever we have, it grows way faster than whatever the write traffic that we have. So in that kind of situation, how do we handle such massive load read loads that we are receiving without even crushing our private database? So that's the pattern. So let's try to see what that pattern is about and discuss. So the problem here, like I just specified, it's a read heavy traffic. So consider any application that we're using. So it can be YouTube, X, Reddit, or LinkedIn, or Insta, whatever it is. So all of this platforms you see obviously the feed. So whenever we open our respective app, definitely from our developers or system standpoint, we are hit with dozens of the videos, Twitter articles, or like Twitter posts, or any posts and Reddit articles, or so whatever it is. So each would require multiple database queries. So to fetch if it's a YouTube, it's a video metadata, and the channel information, user information, the likes counts, the subscribers counts, and the comments, and all those things. So that's just I'm just laying out such scenarios. So that's potentially something like it can be like hundreds of 100 plus read operations just to load particular feed on our platform. And meanwhile the write ratio, it might be just we post one photo or one video, or like occasionally, or whatever it is, write one Twitter post or whatever it is. So this basically, it's very common in majority of the platforms. So for every video created, for every tweet posted and everything, the scale ratio, read scale ratio is obviously 10 times higher, 100 times higher than whatever the write ratio is. So thousands of users read it, and even like consider any product, any application. So any e-commerce website, whenever every product is uploaded, hundreds of people, thousands of people in big magnet or browser, same applies to YouTube and everything. So that's the problem. So the read traffic is more than the write traffic to our server. So in the ratio, it will be in the ratio of mostly 10:1, 100:1. So how do we deal with this kind of situation? So make sure that the servers whatever we have, they don't crash and they don't go down. How do we handle all of these situations is what this pattern is all about. So what are the solutions then? So this is the problem that we identified. So let's try to see what are the ways that we can think of whenever we are put under this kind of situation. So scaling grids, so we can solve it with the three approaches. So let's try to see what are those approaches at a high level, and then we'll try to break down into each approach and try to elaborate more on that. So first is basically try to focus on optimizing in our DB. So it can be indexing, denormalization, vertical scaling. So we'll talk about what are they in detail as I elaborate of each approach. The other option that we can think of is basically scaling out. So here introducing read replicas and trying to shard our databases and all that stuff. The third thing is basically adding the cache layer between our database and server. So it can be application cache or CDN or edge locations, and so those are the like three approaches, the solutions that we can think of. So let's now try to discuss this first point, optimizing within our database. So first thing is indexing, like I just mentioned. So basically what is indexing? So let's just try to take simple analogy. So assume like it's a simple sorted lookup table. What it does, that really helps us to point to rows in our actual database. So like normally we read books, right? So like let's say I wanted to find specific chapter or specific section, we mostly try to look in the index section. So instead of scanning every page to find that exactly whatever we are looking for, so we check that index, and then it helps us to navigate to correct page or so for that section whatever we are looking for. So same applies to our database. So whenever we try to query, assuming we don't have an index, so this database, what it does, it tries to read every row, meaning it tries to do every full scan of all the rows that we have in that table to find whatever we are looking for. But assume like we have an index, so what it does now, it can jump directly to relevant rows, like this what it does, the order of n, the linear scan what we were doing, it can change that into log of n operation. So that is basically, instead of, let's say we have millions of rows, so like instead of scanning 1 million rows, we just now check in the 20 index entries or something like that. So this is how it's going to look like. So basically we try to this assume like this is the memory. So here we first try to get the index. So this is the disk. So assume that we are trying to get the index. Once we get that index, we try to look up the right page from that index. So let's say we try to look for that specific page. It might be page 7 or page 6, just a random representation so that it is easier for us to understand. So this is something that we can focus on to improve the read operations or performance. So even in this indexes, we have different types of indexes. Like mostly we use B-tree for general queries, and there are hash indexes as well. They're mostly used for exact matches, and we have specialized indexes for full text search or geographic queries and all. So that is something again a discussion on its own, but that's a rough idea of what it is. So that is what. So first thing that should come to our mind whenever we are receiving higher traffic, first check is do we have an index on the frequently accessed columns or so, and all those things. So that's why so basically better to index on a column which is being frequently accessed by users. Then that really improves the lookup time and all those things. So that's the first approach. And now the second thing is we can think of is as a quick workaround is hardware upgrades. So sometimes what we try to do is basically we try to increase, let's say our the hard drive is having 4 GB RAM and 50 GB disk. So adding more RAM means that now our data can sit in memory more instead on disk, and faster CPUs and more cores meaning that it can now return query very faster to the users whoever is trying to ask. So that way is something that we can think of before we really try to figure out the optimal ways in an approach or so. So this can be a quick way as an hard fix or so to handle every read traffic till we figure out actual way to make it more performant or so. So this is one thing. So we can just right away upgrade our hardware, maybe adding more RAMs and more disk size and all those, more CPU cores and all those things. So that's the another approach that we can think of as a way to handle this the scaling reads thing. Then the third the approach in first one is basically denormalization. So here we know what is normalization is. Basically that's like we try to structure data in separate tables or so to reduce redundancy and and to avoid storing duplicate data. That definitely helps. So because that really helps in saving some space that we need in a storage, and also It saves storage, but the other way around, it makes queries more complex, meaning now we need to do multiple joins to bring data back together from across the tables and all. So that's one thing. That's the normalization ideally. So that is the case when we have like balanced read and write traffic. And for read heavy system, it's okay to go with denormalization. So basically the quite opposite of normalization, where it's okay that we store redundant data, because here we're doing trade-off of like storage for the speed of retrieval. So now what we do, instead of doing multiple joins to get, like, let's say the examples here, we have customers table, orders table, and products table. And let's say we wanted to get the users related info. This is how normally we do. If it's we have followed clean normalization and all. So we try to query the customers table and join orders and also join products, and let's say we have other order items and other tables that we have. We'll try to do multiple joins on these tables and get the all the information that we need related to that specific order or user profile or whatever it is. But let's say if I denormalize and I try to decide to create one table called order summary, so to get the order profile for a particular user. So this can be something like this. I'll try to have this table with directly I store username, the location, and the date, and the product and the cost of that. So now whenever I would like to get the details for viewing the orders and all, I can directly query using this columns that we have: customer name, order date, product name, price, from this table. And so there are no multiple joins or so, and it makes read more efficient. Of course, the trade-offs is like whenever we do some updates and also the write operations, now we need to make sure that we need to do this at multiple places in this table and other tables that we have and all. Again, that's a trade-off whenever this read traffic is very high when it compares to write traffic. So that's one thing. So and also, like, this is the one way of denormalizing to handle this read traffic. Then mostly let's say people are looking for analytics related queries and they wanted to see, and for that kind of situation, so basically where we need a pre-computed expensive aggregations and all, people try to create materialized views. So let's say, for example, let's take an example of an Amazon itself, like e-commerce products. So whenever we wanted to calculate the review of particular product, like it will be basically average of that product ratings across all the users whoever has given, right? So instead of trying to calculate that average on every page load, we can compute them once, like via some background job or so, and store the results. So this way now like and expose that as a materialized view, and whenever we wanted to now get the product ratings, so we can just use that materialized view as, like, let's say product underscore ratings to get that, and use that to showcase in the product page, instead of trying to read and doing this calculation of rating across all things like with average or so, and showcasing instead of that. So this way, like we try to reduce the load on our DB if it's a read heavy traffic. That's the this thing that I was talking about, materialized view. So we try to pre-compute this expensive aggregations via background job, and this basically we try to store in this way, and we just now do this lookup using this thing. So yeah, this will be a scenario just to avoid that. Yeah, that's like the first approach, or the first things that we can immediately think of. Now let's go to the second the approach that we have listed down. First thing is trying to introduce read replicas. So what do we do here is basically we now try to scale behind a single database. Is adding more ways to copy data from our primary database to additional servers. So the idea here is basically whatever the writes happens to in our application, they primarily go to this the primary database, whatever we call leader or so, and then this reads will be slowly propagated to all the followers that we have to the other databases. So now whenever user tries to request for some data or so, now we will not divert that traffic to this primary database. This handles only the writes. The reads will be served from all these followers. So this way we are trying to delegate the traffic to multiple databases, which is the read replicas. So, and also even this not just in handling this fan out of reading traffic delegation, but also here it handles in case of redundancy, meaning let's say this leader failed. So that way whenever it failed as well, for write operations, this can be any of these followers can be promoted as a leader, and the writes will still be handled and will not lose any data. So all the read and write operations will be going smoothly as usual. So that's the thing. So that's how we try to handle. And also here we have asynchronous updates and synchronous updates. So here basically asynchronous in the sense what do we do, writes will happen but still followers will have the stale data. That's fine. Eventually we'll try to be consistent, so maybe in the batches or some background job we'll try to copy this into data. That way though the read replicas might serve some amount of time stale data, but eventually end users will see updated data. If it is a synchronous, so what happens in that case, we first write it to leader, as well as along with that we need to write all that to the its followers as well. Only then we acknowledge to the client. So this way now all remains consistent, but the only thing is it adds latency to the users or whoever is experiencing and all. So they're also what are the situations where synchronous consistency is needed, asynchronous consistency is needed, and that way we need to decide which one to choose. That's the read replicas approaches. And the other approach is basically sharding. So here we know that above read replicas that we just discussed, they distribute load, but actually in reality they don't really reduce the data set sizes that we have. Basically it will be exact copy of whatever we had in a primary database and all that stuff. And now assume our database grew so large that even all the steps that we followed above, indexing, denormalization and all, still doesn't help. That's where now we need to think about how can we split into based on some functional or so that's again trying to divide into smaller pieces, so that particular group of users will be served from that specific shards. So here let's talk about first one, functional sharding. So here basically what we do, we try to split the database by domain or feature. So here let's say the server all orders related thing, I'll try to put the data in that DB, and all the data related to customers I'll try to keep it in the customers DB, and for reviews in this way. So basically the idea is here is to shard or split by domain or feature, so that now each request related to that specific feature or domain, it's that specific DB, rather than all keeping this in a single database. So that's how we try to shard it by feature or so. So that's functional thing. And the other thing is basically trying to shard it by geography. So here is basically, let's say our application is popular and it has a global appeal, and we have global users presence. So what we try to do now, the DB related data, so whatever the data that we have for specific user let's say user is from US or UK or whatever it is, so we'll try to store in that specific region itself. US related data will be stored in something like US region availability zone and that specific region, and same way Europe related users will have their data stored in that specific region DB, so that now each region's data lives very close to its user, and whenever it's trying to retrieve, the latency and the turnaround time will be way faster than trying to store in some different region. So that way we try to shard in this way, so that the specific region's users goes to that DB only and not to other DBs. So this way, like functional and geographic sharding, we can try to think of even whenever the approaches that we discussed before, like indexing and the other things, read replicas and all. This is the other approach that we can rely on. So fine, so that was the second thing. And now let's talk about the third one, the adding the caching related layers. So here we have assumed like we have optimized using approach 1, approach 2 and all those things, but still we need more performance also. That is where we have to think about this caching and all. So basically what caches really helps us with is basically they provide a better performance for very read heavy workloads. Because most of the platforms that we see that we use as well, they experience very high skewed access patterns. Let's say like most viral videos are watched by most users. Same thing on Twitter, viral tweets is read by millions of people. So you understand the point here is like, right? So it has like very high skewed patterns. So even like even in any of the like e-commerce other platforms, popular products are viewed by thousands of like millions of people. So what does this really conveys? Basically we are querying our database for very similar data, like identical data. So basically the data that is rarely changing between requests. So that is where like the data that is rarely changing between requests from multiple users, that's where like we need to think about the caches introduction. So that's the that's where it helps really. So just trying to store frequently accessed data in memory, and whenever we have that, we try to read it from memory instead of from the disk that we have in our DB. So that's the thing. So let's talk about now the application level cache. So this is standard pattern wherever we see. So basically here we have the server. So what we do, we will have some Redis or memcache or whatever it is between our application and the database. So first we try to check in the cache if it is there. If not, only if it's missed, only then we'll try to read that and then populate the cache. So the next time again, whenever we first check the cache, we try to retrieve from that. So this is the application level cache. So this works fine most of the cases. And here again the caches, we have like multiple invalidation strategies. So here what do we what are the approaches that we normally follow? Like make sure that caches always have the up-to-date data and they don't really serve stale data and all. So what are the ways that we can follow, like eviction policies and all? So first thing is basically time-based expirations, so TTLs. So what do we do in this case? Mostly we'll try to have this TTL of 5 minutes or so, and post that will be removed from the cache, so that now we ensure that at least we don't serve the stale data. And the other approach is basically write through invalidation. So here what we do, we try to update or delete whatever it is from our cache immediately after writing it to the database. So this way it ensures consistency but adds a little bit of latency for write operations and all. Again, that's a trade-off. So and the other is basically write behind. So it's simple. We'll have some asynchronously some queue or whatever background job. It tries to sync between database and the cache, and try to make sure that cache is having up-to-date data. So it's asynchronous again. But it's quick, because we are not waiting for the cache writes, right? And the other approach is basically tagged invalidation. So we'll try to keep the keys grouped by tag. Let's say user 1 to 3 videos or so we'll try to invalidate all these entries with that specific tag when that related data changes. So that way it's really helpful for very very complex dependency, but it again requires us to maintain this tag relationship and all, but that's one way. And the other is basically versioned keys. So we'll try to include version number in cache keys. So every time any updates or anything that changes, we'll try to increment that version, and so naturally the older versions will be invalidated, and again here we need version tracking and all that stuff. So mostly in real systems we try to use combination of TTLs and try to follow some other approaches that I just mentioned right behind. So combination of one or two mostly, and then try to meet the requirements of whatever the system that we are currently designing. So that's the thing. And it's important thing is how do you decide even the TDL for specific application. So that's also one of the point that you need to lay a bit of attention on. Let's say let's say in Twitter or something, let's say I'm updating my photo or some username or so, and if the requirement that we have, it's okay if user can see stale data for 5 minutes, and then we know that 5 minutes of TTL or something like that. So that's how based on the requirements and proper understanding of the system that we are building, TTL has to be decided upon. That's all the invalidation strategies for caches and all, and that was our application layer. So now let's discuss about on the CDN and edge caching section. So here what we do, these CDNs they try to help us to cache this shared content at global edges. So what do they do now is basically users can read from the nearest edge location instead of reading it from the region that we have stored. So this way anything loading of images or videos or something like that, this let's say user from US can use this edge location to read that specific content, and instead of getting it from the original region or whatever we have. So that way introducing CDNs and edge cachings is basically helps us to reduce this read latency issues, and also distributes the read traffic to this global edge networks that we have normally provided by cloud providers. Fine. So those are 3 approaches that we can think of, and that's how we try to deal with this pattern. So now the thing is basically when to use what and which approach to follow and all those things. So first of all, we need to identify in our design or system that we're trying to deal with, try to identify the one which is having high volume. Let's say we are building an API, so let's try to see which endpoints are receiving high volume reads, and try to first focus on optimizing that one. So that is the thing. So basically we need to first identify a spot, the very read heavy endpoint, and then we need to estimate how many reads are happening per second, or so what's our capacity, and then we need to think about all the optimization steps that we just discussed. So first try to prioritize indexing within the database, and trying to add caches in between between application and our DB or CDNs or whatever, and then think about adding read replicas and sharding and all those things. So here basically this order really matters. So try to focus within database, do not try to complicate it. So query optimization first is our preference, and then caching, and then only replicas and sharding, because the simpler the better first, and then try to complicate things. So that's the thing. And now common scenarios in our discussions whatever we had. So URL shortener, so that was like extreme read write. I think if you hadn't had a look at that discussion, you can just go and look at it. So that's like a scenario where it is really heavy thing. And same way here, book my show, district, or whatever event related booking platforms. So people try to see which seats are vacant, or like is it open, or like how many are booked and all. That's also very read heavy kind of systems. Same thing, news feed, we are trying to read any news feed or Twitter feed or any post feeds, what are all the social media platforms that we use. And video platforms, reading posts and watching videos and all those things. So these are all the situations mostly have this pattern of like read heavy traffic and all. So these are like few examples that we can really connect this pattern to, and that's the scenarios. These are the scenarios that we really need to think of, the approaches that we discussed above. And yeah, finally that was like when to use and now when not to use. Also it's very important to understand. So basically don't try to think about these patterns approaches whenever it is read light and write heavy. So here let's say Uber related, so it has like location updating. So write is very write heavy because every 5 seconds or so we need to update our locations of our drivers, and so that there we need to focus on how can we scale these writes, not the read. So and also like the whenever the consistency is very important in case of like payments, inventory and all. So there it's something we should not focus on read, but instead focus on writes. So and all those things. And and the small scale, let's say 1K users, we have a single DB trying to tune that, that should be fine. And even this real-time collaboration related scenarios are so scaling reads pattern is something it's not feasible. So these are the scenarios, like small scale applications like write heavy location updates, and strongly consistent systems like payments related or inventory, or collaborative systems like Google Docs, and anywhere real time is involved. So don't even think of this scaling reads pattern, and this is not suitable for that. So that's the thing. Basically not to use in those kind of situations. So here let's try to take couple of the scenarios. So let's say like we are seeing that queries are slowing down as dataset grows. So what is the immediate thing that we need to think of is basically we try to first add an index. So without an index, what we do for every lookup, we do full table scan. That is why queries are slow. So whenever we try to add an index and a column, so we are querying very frequently. So let's say like I'm querying on this or customer ID. So after index scan, so I do like instead of doing let's say on million rows, I do some lookups on 20 rows or so. So that way like we try to first add an index on a column that is frequently accessed, and try to speed up this queries return time. And if you're trying to rely on multiple columns, we can add an index on the columns in the same order that we are trying to retrieve from. So that way it really helps us to make the queries faster. So fine. So the other scenario is, let's say, like, we have millions of concurrent reads, for the same cache data and all. So let's say, like, a popular personality posts something on our platform, and now suddenly all of his followers are trying to read it simultaneously. So ideally one cache can do what, let's say, like 50k requests per second, and so now they're getting like 500 grand or like 1 million requests per second for that single key. So now this cache starts timing out and requests fail, and our site goes down and completely. So this is basically the hard key problem. So first fix is basically we'll try to coalesce the request, meaning try to batch the request whatever we are trying to get. Instead of making one request for every query that we are receiving, batch it for, let's say, calls. Let's say we have like 20, we are trying to batch it, and we make one request for this 20 queries whatever we are receiving. So this way we will try to avoid hitting the cache for every same request that we are receiving. And so yeah, that's the pattern. We'll try to combine multiple requests and all into single request, and this way we reduce this. Even when that is not enough, now we need to distribute this hard key whatever we are talking about. So that is called hard key fanout. So here what we do, we'll try to store the key itself as n copies. So now clients can pick one at random, and now we are trying to spread load across the cache servers. So here this is what I mean. So this key, we'll try to split it with the additional the key we are trying to add, like this hard key 2, hard key 3 and all. So now the client can pick from any of these keys that we have, so that every key now is serving same data. So that's how we are trying to distribute even the hard key into multiple keys to the clients. So that's one approach to avoid this hard key problem whatever we have discussed. Then the other scenario is basically how do we handle this cache stampede. So here the situation is basically whenever the hard keys, whatever the TTL that we have is expired, and now we are serving everything from that cache, right? So all of a sudden now they will try to hit our DB instead of, because cache is a miss. So now every request is missing all at once, and it tries to slams this DB. So that is where now again the other approach is basically probability early refresh. So here what we do, every read request that we have, let's say assume that we have TTL as 60 minutes. So every read that we receive, will try to increase the chance to refresh early. Let's say like we have 50 requests or so, so we'll try to refresh 1%, and same 55 requests 5%, and like that we'll try to make sure that based on the request count that we are receiving, we'll try to refresh this way probabilistically. So here again all, let's say 100k requests are missing at minute 60. So that is like last thing, and DB gives up. And so the alternatives again here is basically having some background refresh job, so that we do it in advance, like maybe 10 let's say 50 at 50th second itself we try to do this refreshing and all those things. That way we can try to avoid this stampede related things, everyone is trying to make a request at the exact expired time and all. That's one situation. And now how do we handle this invalidation. So when data updates need to be like immediately visible, so like even they can't tolerate like some stale data even for a short span of time. So that's where like cache versioning we need to think of, like I mentioned. So basically we'll try to maintain multiple versions for the same thing, where with every update the version increments and the lower ones will get invalidated, and the information will be stored from the latest version, such that the immediate updates, even the cache invalidation, will always showcase the latest information up to date in a immediate way. So that's the one thing. So we'll try to bump the version in the DB as well, and then we try to route to the new key, and that way like so only thing is basically we need to worry about maintaining version state in our DB, and then check for proper updating and syncing between cache and DB. So that's thing. So on write, what we do, we try to bump version in the cache as well as DB, assuming like we are doing in transaction also. And now this let's say new key, old key was like order 789 v56, so now it becomes v57, and same thing we'll try to store in our DB as well, something like this version 57, and so this way again we'll try to keep it and make this as immediately visible to the end users. So these are the ways or the things that we can think of to handle this scaling reads pattern. So to conclude, this is what the clean progression or the picture that should be in our mind. Try to first try to do optimization within our DB, like indexing, denormalization and all that stuff. And first, so even if that doesn't serve, then try to scale out horizontally, adding read replicas or so. And even if that didn't serve after read replicas or sharding, then introduce this caching at application layer, and also the CDNs. So on invalidation, like I just said, try to follow any of these things and handle all these scenarios of hard keying and cache stampeding and immediate visibility and all those things. So these things is what really matters, and the adoption, the linear progression, this is how it should be. So yeah, first, like always, the principle should be trying to start simple and then prefer all the approaches that we described. So this is all about scaling reads pattern, and the next one will be scaling right. So let's jump on to that.